In the last video, we went over rules of exponents, and we did that for our purposes in Chapter 6 in order to be able to understand rational exponents. So if I have an expression like a raised to the 1 over n power, or the 1/nth power, well, that's equivalent to saying that I want to know what the nth root of a is. So with this equivalence, what we can do is we can convert back and forth between the different notation, and that might help us to manipulate some of it. For instance, if I had something like the number 27 and I want to raise that to the 1/3 power, well, I know that that means that's the cubed root of 27, and that the cubed root of 27 is 3. And I mean, while it might not be, it's just as easy to go from the third root of 27, or 27 to the third power, to 3. What being able to convert between these two different notations helps us do is something like the following. Let's suppose, rather than just knowing what the cubed root of 27 is, which is easy, that's 3, let's say I want to know what the cubed root of 27 squared is. Now, 27 squared is a pretty big number, and I don't really want to multiply it out and then try and figure out what the third root of it is. So let's manipulate it. Let's change it to the this notation here, this rational exponent notation. And when we do that, we have to remember that the index number is the denominator of our rational exponent, and that the exponent here underneath the radical, the exponent of the radicand, as it were, is the numerator of my rational exponent. So I can rewrite this as saying 27 to the 2/3 power. And you might ask yourself, well, how did that really help me any? I mean, it still looks kind of weird. And I agree that it does, but if we invoke our rules of exponents, then we can unpackage this a little bit more easily to evaluate it. For instance, I can rewrite this expression as 27 raised to the 1/3 power, and I can raise that to the second power. Now I've invoked one of my rules that we learned in the last video, which is the power rule. I just did it backwards. Instead of multiplying this exponent here to this exponent here, I divided that exponent out, and now I have something that I recognize, because here I mentioned that 27 to the 1/3 power. Well, that's just 3, isn't it? So what I really have is 3 raised to the second power, and gee, that's pretty easy. I know that 3 times 3 is 9. So if I take the cubed root of 27 squared, rather than multiply 27 times 27 and then try and figure stuff out, I can just unpackage it using my rational exponents and say that it's just 9. And you might ask yourself, well, how do the other rules of exponents apply in this case? What, for instance, would happen if I had, I don't know, let's say 9 to the negative 1/2 power, right? Well, it would apply in exactly the same way. 9 to the negative 1/2 power, you would have to take the reciprocal of 9 and raise that to the 1/2 power, and we know that 9 to the 1/2 power is another way of saying the square root of 9. Remember, an index of 2 we don't write out front, and because out front of the radical, and because the square root of 9 is a number, then we would leave it as 1/3, or 1/3. So negative rational exponents work exactly the same way as any other rational exponent. And so what if we're asked a question like, write as a single radical expression a to the 1/2 power, b to the negative 1/2 power, and c to the 5/6 power. And so we want to convert from a rational exponent into a radical expression now. We want to write it as a radical. So the first thing we have to do is, well, in order to have a radical with one index out here, we need to be able to understand this number and this number as the same index as this one. And the index here, c to the 5/6, is the 6th root of c to the 5th power. So let's rewrite this whole number with everything having a 6th power. So a to the 1/2 becomes a to the 3/6 power, because 3/6 is the same as 1/2. B to the negative 1/2 would be negative 3/6 power. And c to the 5/6 would stay as c to the 5/6 power. Now I have everything in terms of one index, so I can rewrite my thing as a radical to the, what is the 6th root now of a to the 3rd power, b to the negative 3rd power, and c to the 5th power. So this is just manipulating radical expressions and using them to translate between rational exponents and radical expressions. Let's try one more. We want to use rational exponents here to simplify this expression. It says we want to know what the cubed root of p q squared c raised to the 12th power is. And that's kind of a lot to take in all at once, but really not all that much when we know that we can translate this into a rational exponent, right? If we take p q squared times c, and instead of taking the cube rooting it and then raising it to the 12th power, let's raise it to the, remember this index is the denominator and this number is the numerator. So now let's raise it to the 12/3 power. Well, that makes it a lot more palatable, right? Because we know that 12/3 is the same as 4. So what I really have is p q squared c raised to the 4th power. And now we use our rule of exponents, our power rule of exponents, basically to distribute that 4th power to all of our factors. Remember, we couldn't distribute a 4th power to terms. We can only give it to the factors. So that would be the same as saying p to the 4th power, q to the 2 times 4 is 8th power, and c to the 4th power.